a nice curiosity, one of the multiple states that the Taylor-Couette system exhibits, except for the following set of experiments. One is Prigent and Dauchot in 2002 extended this system by making the gap much smaller. And we're able to see that what was this spiral pattern, this barber pole turbulence, in fact, if you make the system very, very large, in fact, is part of a very regular pattern of turbulence. So the turbulence actually organizes into a very large scale pattern, quite regular, very persistent. And this is how I got interested in this, but I don't come from the world of turbulence. I come from the world of pattern formation, nonlinear PDEs and so forth. And I looked at this, and this is a highly fluctuating pattern, and quite intriguing to be able to understand that. And so one of the questions that I would like to be able to answer, and we're getting close now, and I'd like to be able to have an answer by the end of my time here, but I think that's unlikely, but maybe by the end of the year. I would like to be able to tell you in a few words what sets that angle. That's what I would like to be able to do. Yes. Yes, that's what you're seeing. This is where the turbulence is, and this is where it's quasi-laminar. Yes, and it's nice that you asked that. I'm not going to talk about too many other flows, but sometimes in this world, sometimes the turbulence is dark and sometimes it's light. It depends on the method of visualization. You can often tell from the way which looks more fluctuating, but it's not obvious. And then the other thing, which is actually more important, and which is really what's driving a lot of this, is that if you make your system even larger, and you begin to ask questions about transition, critical points in the route to turbulence, these stripe patterns, they become fragmented, but they are the key element of the route to turbulence. Okay, and I'm going to describe that to you. All right, and so that's kind of the reasons that we're looking at this even today. So I want to. Theoretically, it's much nicer to do the planar case than the circular case. So this is plane Couette flow, and it's the same group of experiments, Prigent Dauchot in the early 2000s. So this is now plane Couette flow. So, and I made one. So, and I did this for two reasons. One, it's nice, But so you have one plate moving one way, one plate moving the other way. But this is the aspect ratio of that experiment. Okay. So I just want to point out that the scale. So that's the depth of the fluid. And so the scale of the pattern is very large on the scale of the shear. So in terms of the gap between the plates, that's a very large scale pattern. And so that, I think that's relevant to the kinds of things that people think about and talk about at this meeting. Okay, so it's a very large scale phenomenon. It's also true in the Taylor-Couette, just wrap it around. Exactly, just that's your Taylor-Couette, just like that. Okay. Okay, so that's what we like to do. We like to be able to describe this flow. And just to show, this is a movie. This is from Duguay, Schlatter, and Henningsen. And in this case, well, you can see this is the turbulence. This is the turbulence, and this is the quasi-laminar. And you see that there's angles here. Of course, you have defects in the patterns. Sometimes it will anneal and become just a completely regular, and sometimes not. Sometimes fragmented, sometimes not. I'll just have you point, you'll notice that the angle is distinctly less than 45 degrees. Typically in plane Couette, you'll see it at about 24 degrees is the nominal. Yeah. Oh, yeah, most definitely. That is correct. But it's thought to become less and less relevant in the narrow gap limit. Yeah, good questions, right? And you're happy to ask as many questions as you want. I can stay here all day. No, and I don't want to do this. So I just want to tell you that this is generic phenomena. You have a wall-bounded flow, something confined between plates or disks or something, and you go down to transitional Reynolds numbers, and it's very, very typical that it segregates into turbulent and laminar regions, and there's a tilt to those and so forth. It depends on the geometry. I don't want to really describe these in detail. The only other case I do want to say, and I will talk about it, is pipe flow. So if you constrain it completely, so it now only has one large dimension in which to form, you get just these turbulent regions. They can't have any other structure. They're just, and then the pipe, they're known as puffs in today's terminology. In case you know this, Reynolds referred to them as flashes, but now we typically use the word puffs. And so they're local, I mean, they're just patches of turbulence within the pipe. Okay, so that's the analog of what I've been talking about here with these stripes, or this barber pole just becomes these puffs in pipe flow. And the rest of the flows you don't need to worry about. Okay, so let me give you a little bit of background, and it's going to be, probably 50% of the talk or more on transition to turbulence in what are called subcritical shear flows, these wall-bounded flows, the channel, the pipe. Plain co-ed flow would be the ideal case, theoretically. And so we know at low Reynolds number, you have laminar flow. At high Reynolds number, you have turbulence. And if you ask the question, how do you go between those two, that's the thing we want to answer. And I thought I would put this in for historical context and, maybe for some of the younger people so that they recall some of these things, or if they haven't learned it. So these ideas date back to Landau, a famous paper in 1944, and Stewart, who did the kind of rigorous analysis of the Navier-Stokes in terms of bifurcations. So you think about how, the question, you go from laminar flow to turbulence, how does that happen? And the simplest idea is that you come along, this is Reynolds number, it's not labeled, and this is some amplitude distinguishing states, and you come along and there's some first bifurcation, an instability of the flow, and it gives rise to some new state. And that state itself then undergoes a bifurcation, an instability, secondary bifurcation, often referred to, and then you get another state, et cetera. And this was the picture that Landau put forward in 1944, and essentially at the same time, Hoff had the same idea, is that there can be a sequence of these, possibly infinitely many, each one introducing a new frequency into the problem, and then after some time, possibly infinitely many of these, you have a complex situation, we'll call that turbulence. You have a broad spectrum of frequencies, okay? Mike is shaking his head. No, it is not the way it works. Okay. All right. So of course, then we know that picture was modified and controversially in the 70s with the idea of chaos and strange attractors. And I also want to point out the idea of universality came in and was very key. The idea that these complex systems do have universality associated with them, and that can be measured experimentally and in numerics. And I think that the pinnacle of this was this work by Swinney and Golub. Again, this is Taylor Couette, but now I'm only turning the inner cylinder. They are only turning the inner cylinder. So it's not the counter-rotating case, it's just rotating the inner cylinder. And what happens is you go through a sequence of instabilities. The first instability gives you the Taylor vortices, which I think is generally familiar. Those become unstable to wavy vortices. Those become unstable to modulated wavy vortices. And then after just a couple transitions, you get something that is broadband spectrum. And that was, again, the idea of chaos. And okay, so you can get turbulence through a sequence of instabilities. And that gives a way in which you go from laminar flow to turbulence in a way we can understand in terms of low-dimensional bifurcation, low-dimensional dynamical systems and bifurcation theory. Whether or not that's really describing turbulence, and certainly there was a lot of controversy at the time, and I think it's clear that that sequence tells you something about how you get there, but obviously it doesn't describe really high Reynolds number turbulence, the kind of questions that you would ask there, but nevertheless, it tells us something about how that happens. And this was extremely successful and extremely influential. And unfortunately, I think it hindered our understanding of transition in the subcritical shear flows like pipes, because there was too much of a temptation to think in terms of this view. And this view is not the way you should think about transition in pipes and channels. It's really not a useful model. So, and the thing is, so the first thing is turbulence appears abruptly in these systems without laminar flow becoming unstable. And I've shown here, sorry, I kind of messed around with my slides this morning, so I'm not sure what the next slide is going to be. Let me just show here. So this is the standard kind of way I would explain it, that if you look in pipe flow and you can measure friction factors, just it's how much pressure gradient you have to apply to force a fixed volume of volume flux of fluid through the pipe, okay? And you do that as a function of Reynolds number. And there's a branch that laminar starting at 0 Reynolds number, and it comes along. And that solution, that parabolic solution of laminar pipe flow, never becomes unstable. And I believe it has been proven, certainly there's a claim, there's a proof now that it goes to infinite Reynolds number. Certainly we know it at least goes up to 10 to the 7, ridiculously high Reynolds number. It is linearly stable, right? So if you start on that parabolic solution, really on it, you'll stay there. Obviously an experiment and a little bit of noise can drive you away when you get to high Reynolds number, but nevertheless it is there. And it's certainly a solution to Navier-Stokes, and it is linearly stable. However, beyond a certain point, turbulence takes over, and it's a disconnected branch. So you have a turbulent situation, right? All right, so the description of, let me just see what the next thing I'm going to say. Oh, yeah, I'm going to give you so before getting on to Landau, let me just remind you what a hard okay, I'm not sure which. All right. What? Yeah, let me do this first. This is a little bit too elementary for this audience, but nevertheless, I've done it. So, I think a tape measure is a nice example of this. So that's Reynolds number. I increase the Reynolds number. That's laminar flow. That's turbulent flow. So I have two states, right? And it's reversible. So if you can control turbulence, you can get it back to the laminar state. You decrease the Reynolds number, and it's still bistable. There's two states with a, there's a threshold between you go from one state to the other. It's bistable. And then you go to, a really low Reynolds number, and there's only one state. The turbulent state has disappeared. Okay. All right. So if you want to explain the bistability to somebody who doesn't know equations, that's what you would do. Okay, and so that's our bifurcation diagram, and you could actually do the bifurcation diagram for the tape measure. But we know a similar thing happens if you look in a certain way that one has to be clear about for these subcritical shear flows. Again, I'm taking some amplitude measure of the state, Reynolds number. There's this laminar solution that exists at all, Reynolds number, and is stable. And then beyond some threshold, which is typically on the order of 1,000, depending on how you measure Reynolds number, there exists a separate solution available to the system. Okay, what's the next thing? And so this leads to this idea that here, unlike the Taylor-Coët, the Golub-Swinney thing where I showed you this sequence of transition, here we have this discontinuous route to turbulence. Okay, and that's where now I'm going to go back to this. And so let's just. Yeah, he just told me how to do it, but now he took the control. All right, never mind. I'll just. This is fine. So if you look in your copy, you go get any edition of Landau and Lifshitz of fluid mechanics, and you go to the page on pipe flow, you will find this description. They don't write down the free energy, but they use the words to describe it. And they will describe how you go from here to there and in what way it's discontinuous. So you imagine there's some sort of free energy and some sort of amplitude measuring the amount of turbulence here at 0. So this is laminar flow. And there's some sort of there's a minimum there, and that is your laminar state. And that is a minimum, a local minimum for all Reynolds numbers. So that's your locally stable state of laminar flow. And then the issue is, if there's turbulence available, the question is that minimum above or below this minimum? If it's below, then this is the favored state. And if it's above, then this is the favored state. So you can introduce turbulence, and if you're above here, then the turbulence will decrease and you go to laminar flow. And if you're below, turbulence will be the favored state, and you'll eventually be all turbulent. So basically, there's kind of a Maxwell point here, if I can find my chalk. So somewhere in here, the view that's in Landau and Lifshitz is basically you'll go along here to some point, and then you'll discontinuously transition to turbulent flow. And it's clearly stated there in a few paragraphs, and it's almost true, but not really. Okay, so that's the view, and that's been around for a long time. And you can imagine what I'm going to say is, of course, that's not quite true. So there was a meeting here in Cambridge. There we are. There I am. There's Lorette. She always looks the same, even to this day. And so this was in 2008. And so one was trying to work out this situation for pipe flow. What is the critical Reynolds number? What is the minimum? Just think of it this way: what is the minimum Reynolds number at which turbulence is sustained in a pipe? That should be a well-defined question. It ought to have a well-defined answer, right? What is the minimum number such that the minimum Reynolds number such that turbulence is sustained in a pipe? And these are the values from 2000, just before 2008. The reason I'm bringing up that meeting is because at that meeting, this work was discussed, and people were arguing about what was the critical value for the Reynolds number of pipe flow. And I don't want. My point is not to make fun. These were serious studies, and it just shows that this was not the right way to be thinking about the problem. And what was missing, I don't want to leave these people's names, is that, in fact, the problem is the transition is not discontinuous. It's a continuous transition. With a critical point, critical exponents, it's a continuous transition. And this is the thing that was, this picture is missing things. And so what is missing, is the fluctuations. Okay, so now, of course, obviously, Landau and Lifshitz knew about fluctuations, obviously. But what they didn't know at the time, because it just wasn't wasn't known at the time is that when you realize that this, I mean, they would have known this, but they didn't understand the implication of it. See, this is the fluctuating state, but laminar flow is not a fluctuating state. It's what's called an absorbing state. So if the system finds itself these are not symmetric. These are not symmetric. That you can fluctuate out of this, even here, you can fluctuate out of this, but you can never fluctuate into it. You can never fluctuate out of laminar flow. Okay, and that asymmetry is very important. All right, and so that wasn't known at the time. The other thing is it's really spatiotemporal. And that what it turns is you have to take a thermodynamic limit in which you go to large spatial and temporal scales in order to get answers that are independent of the scale at which you're looking at the problem. Okay, and that again was something, and that was the issue with those papers that I talked about before. It was not understood at the time is how crucial this is and how we have to look to find the scale at which we stop being dependent on the scale at which we're doing our measurements and doing our simulations. Okay, and then one other thing that was absent and is kind of important in terms of the theoretical thing is the interaction with the mean flow. And I'll get back to that just at the very end. In terms of developing models, you realize that it is not just about turbulent and laminar, but there's a mean profile that is involved in the flow, and that acts as a slow field. That basically what you have is a turbulent field, which is a kind of fast field, and along with it, coupled to it, is a slow field, which is the mean flow. And it's that coupling which sets the scale of the pattern that we know. And how it sets the angle, we still don't know, but we're getting close to being able to answer that. Okay, so that's kind of okay, so these were the things that were missing. Okay, so let me tell you a little bit about pipe, because it's the thing we understand best, and it's easier to explain because there's only one spatial dimension that we really worry about. And these are sketches that are modeled after what was in Reynolds' 1883 paper. This was known to Reynolds, that at low flow rates, at low Reynolds numbers, this is dye. In my world, these are extremely well-known pictures. I don't know if they're known to everybody, but these are in Reynolds, modeled after Reynolds pictures. So this is the inlet to the pipe, the bell-shaped inlet. There's the dye is injected upstream, and that's your laminar flow. At high Reynolds number, of course, it becomes turbulent after a short distance downstream of the inlet. And then Reynolds, as I mentioned, Reynolds had noticed that kind of in this region where he was just getting, he definitely had turbulent, definitely had in this region here, again, this is about Reynolds number 2000, where all this action takes place, is that he saw what he referred to as flashes. And those were reproduced and known through the 1950s, et cetera. Those were seen in experiments. And you can imagine that because they occur irregularly and intermittently, it's natural to associate them with imperfections. Okay, we now know that they're not imperfections, even in a perfect DNS, fully resolved DNS, that these will occur intermittently, and I'll show you a picture in just a minute. Okay, that's fundamental to the system. Again, it has to do a lot with the fact that it's a fluctuating system. And again, I'm going to call those puffs. Okay, and so this is a DNS of pipe flow, and there's several puffs in the pipe. Well, several puffs here. Okay, so one is below the critical Reynolds number, which we now know or have a very good approximation to, and one is above, okay? And what you're seeing is space, pipe axis, and time. And you're moving, these things are all moving, for me, it's this way, for you, it's that way. They're all moving down, well, it depends on how you orient the pipe, but they're all moving downstream, but you go into the frame of reference in which they're more or less stationary, of course. And you start off, in this case, with 4 puffs for these patches of turbulence, and you let them evolve. And you see that they go along for a while, and then they decay. So in other words, they're sitting over here, and then they individually pop over to there, and they never come back. Okay?
I already see the linear stability reference.
No, I'm going to tell you what it is. I'm going to show you what it is on the next slide. It is the critical point below which turbulence is not sustained and above which it is.
So those things there.
That is right. Those are the initial. And it's to be illustrative of the phenomenon. There's nothing particular about those initial conditions. Okay, it's just to show that if I introduce, so let me just tell you this. If I introduce turbulence everywhere in the pipe within a very short, a few hundred effective time units, and I'm sorry, the scale is not on it. That's many thousands of effective time units. But on this scale of a few hundred effective time units, it would have segregated into several of these, just like this. You could have started just a little bit below this with turbulence everywhere in the pipe, and it very would have quickly segregated into these structures. These structures would have persisted for a certain amount of time, and then randomly, they would have decayed. By randomly, I mean that if you measure individually, you measure the survival time of these, you'll find that it's an exponential distribution. Exponential distribution of survival times, it's essentially a Markov process. It has no memory. The probability of decay over any interval of time is fixed. Okay, it doesn't remember. It just, you tell me an interval of time and I'll tell you what the probability is that it will decay in that time interval. Okay, that's the way these behave. Anyway, the point is, I can explain all that more in detail if it's of interest. But the point is, once I'm blue, once I hit the top of that, the turbulence will never come back. Okay, then that's this idea of an absorbing state. Oh, it says there, absorbing state. So once I fall into that, I'm never going to come back out. Okay, right? Here, I've gone to a higher Reynolds number. In this case, I could have started with several, started with only one. And you see this phenomenon, it's referred to as splitting. It's a proliferation process. We call it's called puff splitting in the literature, so I'll just use that. You know, it's a proliferation process. Another puff is, a daughter puff comes off the parent puff, always on the downstream side in the case of pipe flow, and they proliferate like this. And so there are two basic processes going on, and this is why pipe flow is so nice, is because there's not another spatial degree of freedom available. There's a decay process and a proliferation process. And what you can do is you can individually measure those two, the time scale of those two processes. Okay? You can individually measure the time scale of those two processes. This is also exponential. It's also a memoryless process. Such a good question. And so this is what we did. And I've listed all the authors here because I just want, there's two Avilas. There's Kirsten Avila and there's Mark Avila, both of them. So you can measure the time scale associated with the decay process and the time scale associated with the proliferation process, the splitting process. And if you ignore the correlations, which you're not really allowed to do, but for the moment we can, you'll get those time scales as a function of Reynolds number, and you see that they cross at a certain point. Okay, so let me just say how you should interpret this. So this is the mean time, what a point on here is the mean time at that Reynolds number for a puff to decay, for the decay process. It's the mean time for a decay process. And the distribution is entirely characterized by its mean because it's exponential distribution. So if you know its mean, you know everything about it, okay? So so that's the mean time to a decay event. Is there minutes of D over U? And you'll notice the numbers on that. And this is the mean time to one of these splitting processes. Okay, and they cross up there. And so the way you should think about it is to the left, decay happens more rapidly. So on average, after a certain amount of time, everything will be gone because decaying is happening more rapidly than proliferation, and it will be laminar. Above, you're proliferating more rapidly than you're decaying, and so you will remain turbulent because you're not decaying fast enough to, right? Right near the crossing, there are going to be correlations that come into effect. And so the actual crossing point there won't be the true critical point. We can use models, and the difference is minute, particularly, now you'll notice the time scale of there in units of D over U. So it's 10 to the 7, 2 times 10 to the 7 is that crossing point. So which corresponds to a puff moving 2 times 10 to the 7 pipe diameters downstream, if that's where it occurs. And that was the problem, okay? And you wouldn't want to do this over and over again. There would be no point. But to do it once was important because you want to make sure, you want to see that you understand it. You want to know how to define this. And the thing is, everything that was measured before that was all a finite size effect. If you're only looking at Reynolds numbers here, you see these things. And what basically people were trying to do is extrapolate this data to infinity and say, when did tau go to infinity? And again, my point is not to criticize people's work. It's just, it wasn't understood what you should do. And so you need to go to extremely large timescales in order to have something that is independent of your observation time. Infinity. It doesn't appear. This is all extremely highly nonlinear. These are all highly nonlinear effects. I'm sorry. Okay. The answer. Okay. So I'll give an analogy and then say what I think. So what I think is an apt analogy is a chaotic billiard, and people use this a lot. So and if it doesn't help you, okay, well I'll do another try. Is if you just take something that is highly chaotic, and then you give it put a billiard in a stadium, an elliptical stadium, so that it's chaotic, and then you put a little teeny hole in the stadium. The billiard will bounce around in there for a very long time and come out that hole. And if you look at the exit times, they will be exponentially distributed. Okay, and the reason is essentially that if you have something that's chaotic, you can also do the same thing with the tent map. Tent map is a perfect example because it has uniform expansion everywhere in the interval. Okay, so there's a Lyapunov exponent associated with that, and so there'll be divergence of trajectories, and eventually a trajectory will come around, fall out the hole, and escape. So if you take a tent map and you take the little top of the tent and you poke it out of the interval, you'll have transient times that are exponentially distributed. So what we think is that in Navier-Stokes is that the idea is that there's a long-lived chaotic state, but which there's a little hole that will take you over to here. But because of chaos, because of the Lyapunov exponent, you very quickly lose any memory of what that state of where you were in the past. You have no memory of your past because of the Lyapunov exponent. That's the argument that's usually put forward. There's no proof of it in the case of Navier-Stokes. I don't mean not just no rigorous proof, but I don't even think Michael seems to want to ask something. All right, let me plow ahead. So the thing is, there's universality in this, and this conjecture goes back to Janssen and Grasberger, and I'll just quote here from Grasberger's paper. It suggests another type of universality comprising all critical points with an absorbing state in a single order parameter in one universality class. So in other words, here I have a situation in which I have an absorbing state, this state that if I get into it, I have these fluctuations, it's a statistical system, and there's some conditions which I'll write down at the very end. And what was postulated in the early 1980s is that there ought to be universality, that all these systems ought to behave the same way with regard to certain critical exponents. When I was a graduate student, this was very popular. Lots and lots of models did this, but nobody had a physical system that actually realized it. And I used to have to explain this slowly in a lot of detail, but since the pandemic, everybody knows it, the R value. So you have two processes, the decay process, you get better, and the spreading process, the R value, right? And so, so you have diseases and they spread in space. And so this is the situation. This is the classical thing. And this is the stochastic. I'm not telling you what I'm submitting. It's just a little toy model, but it's stochastic. And the thing is, there's a well-defined critical point such that below that, with probability 1, you will not persist indefinitely. And above it, a sharp critical point, and above it, with probability 1, you will persist indefinitely. Okay, so I remember learning about this when I was a graduate, and I was amazed by that statement. Okay, so there is a well-defined sharp critical point. Yes. Yes. Oh. Oh yeah. Okay. You mean you're saying there's an interval here over which. Oh, but I don't have probability. I don't have probability 0 being state. Oh, really? Okay, I want to talk to you. Yeah, I understand. But okay, I definitely want to talk to you. Okay. So there's exponents associated with this, and you could just see that what increases is the black is the turbulence, So you can see that the turbulence fraction grows continuously from 0. So that's why we have a continuous transition. So when you measure, and people have used turbulent fraction, long before this, people from the 1940s even used turbulence, or even probably in the 30s, used turbulence fraction. That is to say, the amount of turbulence in the flow as the natural order parameter. They didn't necessarily use that word, but it was the obvious thing to measure. So you measure the percentage of black here, and you measure that as once you reach statistical equilibrium. And then you measure that as a function of Reynolds number, and it grows continuously from 0. You can just see with your eye that that's true. And then there's likewise scales associated. You can see the divergence of scales associated with going towards that critical point. And there's a space and a time scale, and those both diverge in the negative exponents. And so those, all right. So and those are the exponents, the universal exponents associated with the transition. Okay, and so they only depend on the dimension of the problem. And by the dimension here, I mean, these are all three-dimensional fluid mechanics, but a pipe would be a one-dimensional problem. And then the plane co-ed flow would be a two-dimensional problem. I mean, there is a third dimension, but it's not relevant to the structure. Okay. And so once this was really realized and understood, there was a real drive to, at least for some systems, to measure this, to exhibit that it really occurred. We were the first to do it in 2 dimensions. I say by we, I mean Matt Chantry did it. And he used what in this field is called Walla flow. I know it's not a particularly good name. It's just stress-free. It's just planar flow driven by a body flow, sinusoidal body flow, stress-free. It's used that, obviously such a configuration is used in many, many situations. But that's the situation. But by not having the boundary layers associated with the walls, it just vastly helps your numerics, and you get the same phenomena. So that's what Matt did. And this is just to show you, this is what's outlined here was the largest numerical simulation to have been done at the time. So that's this size, okay? This was the largest experiment that had been done at the time. And to reproduce this phenomena, and again, now you see again these bands that I started with, these stripes. You don't need anything bigger than that. But the thing is, so Matt made the system bigger and bigger and bigger, and he went to this size. And the reason if you want to simulate that, you don't need a system this big. But if you want to simulate that, which again, as you go towards the critical point, it becomes sparser and sparser. You better have a pretty large system, or you're not going to see the associated phenomena, because if your system happens to be this big here, it's going laminar. Okay. All right. So basically, again, to say this is now, we're now talking about a sheet of paper. So that's now the thickness. That's now the aspect ratio. And again, I don't think this is worth doing for many other flows, but it was useful to have done it at least a few times. And so I'll just show you, massive. So let me go here and just pause it so you can see what you're, oh, no. All right, so what you're going to be seeing is, again, turbulent fraction, the percentage of black as a function of time is plotted in the upper left there. And then there are 3 different Reynolds numbers. That one is above the critical value. This one is below the critical value. And this one is very, very close to the critical value as we estimated, okay? And just to tell you, you'll see this. This one is not done on this full geometry because these are very expensive. It's only done in a quarter. We just repeated it 4 times just so that you could see. All right, there was no point in simulating that. And that power law that you see there is that predicted for the universe. That should be the universal exponent. Oh, sorry. All right, now we'll play it. So these are the 3 cases, and it'll go for a while. And of course, that's logarithmic time. So it's going to speed up here in a minute. So you see these nice stripy patterns that form the elements here. And then it's going to go on. And you'll see that, they're decaying. And particularly this one is really, the turbulent fraction is decaying. It's become whiter and whiter. It'll eventually fall to 0. That one's going to persist. And this one is going to for the length of our simulation, is just kind of decay and decay and decay. So that one is gone now. And even if you put it in a bigger box, it would be gone. And then, you spend millions and millions and millions of CPU hours, and there you go. And again, logarithmic time is hard to, it's very expensive. But okay. And through great work and diligence, Matt was able to establish all the exponents. And I don't think that's of any general interest other than for people in the field. Okay, so that was the first time for a planar flow that was done. But the point is, you really do, the turbulent fraction really does grow continuously to zero. And it is the right way to think about the problem. You can propose other ways to think about the problem, but then everything you propose will depend on what size system and how you do it. This is, independent of how this is the biggest system. And then you can then ask, well, if I made the system smaller, what would it do, et cetera. But it's nice to know what it would do if you kind of go to that thermodynamic limit. Oh, they're numerical values. Oh, no, they're not nice numbers. They're irrational numbers. What am I doing on time? So what time do I end? Okay. Oh, no. I'll be done in an hour. Okay. I just want to make sure it wasn't less than an hour. Okay. So this is then, so they're really kind of there are two ways you can look at transition, and you can find places where they're actually kind of mixed. But there's certainly many situations in which it's useful. In cylinder wake, for example, it's useful to think about through instabilities and getting through turbulence through a cascade of instabilities and how you get to turbulence that way. But then there's this class, particularly in these subcritical shear flows. We see it now over and over again. I've only shown you a few, but we see it over and over again that they behave as in the class of these statistical phase transitions. And I didn't tell you these are stochastic models that we're mapping on. Okay, and it's really you get a sense of what I was emphasizing about the spatiotemporal scales and the fluctuations are really the relevant things that are going on here in terms of the phenomenon. Okay. Okay, well, I got through that faster than I actually thought I might. So, yeah. So now I'll come to the model of the planar shear flow. And this is work done with Santiago Benavides, who will be here next week. And also, I want to really shout out to Sebastian Gomez, who will also be here next week, who a PhD student who told me a whole lot about the mechanics and mechanisms of planar shear flows. And Laura Tuckerman, who will be here next week. So they'll all be here next week. Sebastian will be giving a talk, but on a different subject. All right, so again, and I cut out some slides, but now maybe I regret a little bit, but but I'll just say in words. What we know in terms of models is that for pipe flow, I'll just say I wrote down a model in 10, 12 years ago, purely phenomenological, but it captures that all the phenomena I just described for pipe flow. And it does it by taking into account the interaction with the mean shear. I might come back and say a little bit about what that mechanism is, or depending on how this time goes. But it was purely phenomenological. It didn't come from the Navier-Stokes. It just said, okay, there's an interaction between I have a turbulent flow I have a turbulent state that is basically doing just this, but it is interacting with the mean shear, and so that provides a negative feedback. And so how would that work? And what pops out of if you just write down a generic model that does that, a whole lot of the phenomena pops out. The problem is you cannot extend that. So there's no obvious way to extend that to planar flows, and I can't explain why, but it's not. In addition, it lacks the fact that it's just purely phenomenological, and you would like something based on the Navier-Stokes equations. Okay, so what we'd like to do is have a model, both because what I want to know is I want to know something about the angle and scales that are set by this. I would really like to be able to answer that question. And I would also like a model because it is useful to it would be useful to have a model for which, I mean, this is extraordinarily expensive, and that's when I had to that's when I went to stress-free boundaries. It'd be nice to have a model that I could simulate in, 10,000 times faster or something that could reproduce some of the phenomena. I might be able to answer certain questions with that. Okay, so that's not, I mean, I think all of that is obvious. But one thing in particular that I care about, but probably misplaced, is a little bit misplaced perhaps, is that if you look at the conjectures in the Janssen-Grasberger conjectures, is the short range interaction. And the models that people wrote down, the model I wrote down for pipe flow had only short range interaction. Again, it was phenomenological, all right? And the issue is that Navier-Stokes are not short range. There's a pressure field, there's a global field. And so it's always been a concern since the times people started thinking about this as a percolation process, in particular, the Janssen-Grasberger directed percolation analogy, whether that pressure field, the fact that it's a global problem and it's not local. Okay, everybody agrees. So the pressure field is a global field. And so everything's coupled together. So if you introduce something up here in your flow, it's not obvious the downstream won't notice it because there's a global pressure field that is going to potentially be sensitive to that. So one of the reasons of having a model based on Navier-Stokes, which has this global coupling, is because then we can begin to think about that without having to do a full Navier-Stokes DNS. Okay, so that's one of the reasons I really want to have something that comes from the Navier-Stokes. Yeah. Look for somebody who's probably there. Well, I think, do you want? Pardon me? Because, I mean, isn't me? I mean, so you get mean field beyond certain dimensions, right? Yeah, 4. So, and below 4, mean field is not. Yeah, there's a Wikipedia article that lists. Okay, so then this brings me then to this. So the issue, and again, this is why the planar flows are so different from pipe flow. Pipe flow is very constrained, and the mean flow doesn't. I'll just tell you. Because I took out the slide, so let me just tell you. It's simple. In pipe flow, and I could write it on the board, but I think I would rather do it with my hands. In pipe flow, basically what you have is where you have the quasi-laminar regime, you have the parabolic profile, and then where you have the turbulence, then you have a turbulent profile. Okay, so we know what those individually look like, and then you're transitioning between one and the other. And basically, all the flow can do is blunt the profile as the mean profile comes into the turbulent region, it blunts. As it exits, it re-accelerates, blunts and re-accelerates, blunts and re-accelerates. That's all it can do. There's not a whole lot of freedom there in terms of what this mean profile can do. I understand it has a certain amount of structure as a function of radius, but basically its centerline increases or decreases. It can't turn directions or do anything very weird. Okay, I mean, I understand it has to deviate a little bit more, etc. But when you allow for freedom in the planar case, it does, and that is very tied to the angle that you have flow up and down along these bands. And it actually, and so this is a DNS of it. Lots and lots and lots of people have seen. In fact, let me just tell you, if you do a DNS, it's the first thing you'll see with your eye is the fact that the mean flow kind of does this along the bands, up one side, down the other. You'll see it immediately. So the most obvious thing you'll see. But what is not shown in these figures, and the reason why, one of the things that has limited my ability to tell you to this day what causes, how this works, is that this is done in the midplane. But see, as you go up and down, you realize that the flow doesn't just have this very simple structure. It's changing orientation as a function of depth as well. And that's why it's much more complicated story than this image at the midplane would lead you to believe. Okay, so yes, the mean flow is kind of turning up and down the bands, but it varies differently as you go through the depth of the fluid. And it's key to what is going on. Okay, so, and I'm amazed it took me 10 years to figure out that this is all you had to do. Okay, but that's life. So all you had to do, so I knew for a long time, for a very long time that the problem was not the turbulence. The problem in understanding it was never really the turbulence. The problem was getting the large scale flow right. And it just didn't occur to me until about 2 years ago. And I should have known because Matt Chantry had basically told me this a long time ago, is that you just need what a lot of us already know, is that you just need a very small number of modes in the wall normal direction. just one even and one odd, just the minimum number that captures the right symmetries, full three-dimensionality. That's all you need, okay? Just take one even and one odd mode. Of course, the wall normal mode, because you have no penetration, only has the one mode, but that's it. So there are five fields that you need to describe the mean flow, okay? And you do need all five, but there it is. So those are the five fields that I'm going to describe the mean flow, and that's the key. And just to tell you, those are going to be described perfectly by the Navier-Stokes. I'm just going to project Navier-Stokes onto those, so there's not going to be any approximations there. Okay. And again, this will be done. What I'm going to do is I'm going to do the stress-free case, body force stress-free. Okay, so I'm body forcing it with sinusoidal body force. So the laminar flow is sinusoidal. And then these are perturbations. And of course, once I have sines and cosines, all the projections are very easy. Do them with paper and pencil. All right, so then I'm going to take as the other field will be the turbulent kinetic energy. Okay, that's going to be my other field. So I have the large scale flow, 5 fields, and then I have the turbulent kinetic energy, which I can also expand into vertical modes, a 0 and a 1 mode. But in fact, for an approximation that it just holds is very well, you can get Q1 from Q0 by just a fast slating principle, and then you really only need Q0. So I only need one turbulent field really to describe this. The second one is around it. I've adiabatically eliminated it, but nevertheless, I only need. So I have 5 fields describing the large scale flow and 1 field describing the turbulence. Two, but I eliminate one adiabatically. And all I'm going to do is plug into Navier-Stokes and then close it through some modeling approximations. There's nothing. It's not rocket science, So let's just go through it though. So that's my forcing. It's a sinusoid. That's what's driving. It's not the walls. It's the sinusoidal body force. I have to put it in Ekman friction because at large scales, if you don't put it in, there's nothing to damp the very slowly varying modes. So you have to put that in. Again, I expand the velocity field in the way and the turbulent field in the way I told you. I don't think. And then these are the things I have to close. I have to close the Reynolds stress. I have to close the production dissipation, and I have to close the turbulent transport. It's, in this audience, I think people know this better than I do. Now, let me just say, so we've done this in 2 ways. I'm only going to show you is we've done it both by trying to be as, we have DNS. We know what, in some sense, we know what these relations are from the DNS. So you could just fit them as accurately as possible. And that's one approach. But we want to keep things simple. So we want something that is, really close to the truth, but also has simple algebraic forms and is generic. I mean, one of the things I should say, as we learned from the pipe case, is that these are very generic phenomena. They have to be. There's nothing, it can't be anything so, you wouldn't think it's such a fine little balance that I have to get exactly this and this right. Maybe, but it's actually just not true. You can model these with pretty simple functional forms. And we've done both kind of the best and then go just, reduce everything, drop everything that just doesn't seem important and just go to the simplest to get the phenomena. And again, those people in Wall-bound and shear flow will hardly be surprised to learn that the only important stress is the U prime V prime stress. That's always the important stress in wall-bound and shear flows. It's not, that's not, again, hardly. I could have told you that before I even started this. And again, we'll just expand it that way. And so to close, we need A of Q naught, and we're just going to fit that with DNS. But in fact, we're going to choose a pretty simple form. I do want to say that this stress does appear. It's quite definitely there. It's not negligible compared to. It's not completely negligible, and if you look at the way it folds into the equations, it's quite interesting. So we've left it out in terms of what I'm going to show you today, but it's the one thing that I would put back in if I were, the next step. I definitely would put that stress back in because it's definitely there, and the way it couples, it contains couplings that are lost when you leave it out. Anyway. The production, there's no modeling now. We know the mean flow. We have Navier-Stokes for that. And once we have the Reynolds stress, the production is, there's no more, you don't have to do any more modeling. That's already determined. The dissipation, pseudo dissipation, again, if anybody wants, I can show the data. We know exactly what this looks like. And we've modeled it with just exponent 1. It actually has a different exponent, but it just is good enough, and we just want to keep things simple. This we just take proportional to Q1. Again, I can go through these if people want later. And then for the turbulent transport, we just use radiant diffusion hypothesis, and we take the turbulent diffusivity to be proportional to Reynolds number. These are pretty standard things. And then you just simulate, you project on the Navier-Stokes and you simulate. And you'll see that it's going to produce, so what you're seeing is the turbulent field. There are no fluctuations here. You can add multiplicative noise or something to model the turbulent fluctuations, but there are no turbulent fluctuations here. And it produces these nice bands. And I don't think I want to, yeah. So of course, you compare, they're not perfect, but again, for the simple, given the simplest model, that this is the simplest model, it reproduces very nicely. I don't think there's that much interest. It reproduces nicely the phenomenon. I want to show you this. This won't mean much to you because you haven't spent years looking at these things, but this is exactly what the bands in DNS do. They flip around like this for a long time before they settle. I'm going to play that again. They're kind of, both orientations are possible, and it'll do exactly this. It'll kind of form one orientation, and then it'll wiggle and kind of flip around to the other. When it flips orientations, it does it by exactly what you just saw in that movie. And this was the thing. It was this movie that convinced me this is right, because this is just what, having looked at these things for years, this is what they look like. Okay, and so then the final thing is, so we have the model, we have it in the paper and review, it's on the archive, I explain all the fitting. But what we're currently working on, and this is in the paper, this figure, but it's where the thinking is going, is again, we had to have a model in which we have the turbulent field, so there are no fluctuations in the model, right? It has 6 fields, but no fluctuation. I can add the fluctuations back in artificially through a model if I want, but there are no fluctuations in the model, which means that when you see these steady bands, there are steady equilibrium to this set of PDEs. And if I have turbulence everywhere in the system, so turbulence everywhere, then that is a fixed point again of the PDE. So I can begin to ask questions like, well, if I had the turbulence and it gives rise to one of these patterns, how does it do that? It does it through an instability. And I have, unlike in the Navier-Stokes, where I have a highly fluctuating field and I don't have direct access to that instability. Here I have direct access to that instability. I can do a linear stability analysis. I have 2 wave numbers, a wave number in this direction, a wave number in that direction. I can measure growth rate of the unstable mode as a function of those 2 wave numbers. And I can find where it first goes unstable. I can find the Reynolds number, the angle, and the wavelength at which it first comes unstable, okay? And so that distance there is inversely the length scale of the pattern you see. And of course, that's the angle of the pattern that you see. And so it reproduces the right thing. And if you look at that angle, it's 24 degrees, okay? It just comes out. And I'll tell you, that 24 is very robust amazingly enough, to the fitting. And the reason I know why it's amazing to the fitting of the turbulence is because it doesn't depend very much on the turbulence. It's the mean flow that is driving that angle. And it's not the turbulence. Almost any kind of turbulence closure that it introduces is that it's extracting energy from the mean flow and putting it into turbulence, that production term. Well, you see it as a divergence of the Reynolds stress in the momentum equation. That's all you need. And so that angle is extremely robust. And so I ought to be able to tell you, and I would like to, within a few months, possibly be able to tell you what sets that angle. But what we can do even now is from the equations, I can just show you the equations. That if I make the long wavelength approximation, and these are long wavelengths, the wave numbers are pretty small. They're not microscopic, but 0.1 and 0.3. So if I assume a long wavelength, that is to say the wave number is small, then I can show with paper and pencil that that angle has to be less than 45 degrees. Okay. Completely independently of how I close this, independent of how independent of the turbulence closure. It only depends on the large scale flow. Yeah. Oh yeah. So I don't have the individual. I don't have the individual. What I'm modeling is. I mean, yeah, because I have the bracket. I'm only modeling the bracket. I'm only modeling the bracket. Yeah. Okay, the boundary condition on in Z, you mean the vertical direction? It's stress-free. Stress-free. It's confined, it's just confined, it just confines the flow from, it can't. Well, yeah, oh, you mean, yeah, that's right. Yeah, that's right. It gives, right, it gives you sines and cosines in the vertical. That's right. It's exactly what it does, which is exactly what I want. That's right. That's what it does. Well, okay, so first, okay, so what is the case is that if you look at all the results published for channels, there's less on Taylor-Couette than you might think, Plain-Couette, et cetera. The angles are all over here, less than 45 degrees. I'm not saying that you never see something. In fact, when you go to low Reynolds numbers, they do begin to approach 45, but they seem to hit a hard wall, which you can even see in this linear stability, that there's something at 45. Yeah. 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 People do not see large angles. You can try and force them in some way, but you do not naturally see them. I'm not saying nobody has ever seen something bigger than 45, but it is highly unusual. Let's put it that way. Exactly. It is described by distribution. You're exactly right. There's a distribution and it's peaked at that's right. You're exactly right. It's not that there's one angle. You're exactly right. And it becomes particularly true. And then let me just say, if you're, there's kind of two regimes. So I'm going to go all the way back here to this. Yeah, this. There's a dense regime in which the angles are the variation in the angles is pretty sharp distribution, but there is a distribution. As you go to the sparser regimes, they become the distributions broaden. That may not be obvious here. Well, no, here, look at that. I mean, well, one thing, it becomes difficult to say exactly, because it's dynamical. These things are wiggling around. You see that? That's actually steeper than 45 degrees, despite what I said that. Guy here, but on the other hand, I don't know where he came from. That may not exactly be a band. That may be something else. Kind of, there's a lot of kind of little fluctuations here. But yeah, you're right about the you're right about that. Yeah. Yeah. Exactly. These are the elementary structures. Yeah.
Some systematic space with the that pattern of bands of turbulent and non-turbulent only emerge by joining up of these.
No, I'm afraid I don't see what you mean.
I could imagine, well, you have a background on top of which there is a payoff. That's the right way.
I think you should think of it as a spatial modulator.
So in other words,
yeah. Yeah. Okay. That's right.
Yeah. So but then the propensity for these angles is which is only
that is correct. So I would say that these are I say these are the elementary structures which percolate. That's what, it's the way I would say it. Okay, so I'm finished. So I would just say that, so it was a good discussion, and somehow I have a final slide here. Oh yeah, there it is. So that's the, so that's the model. That's where I am. I'm going to be, here for a few more weeks. I'm going to be trying to say something more, from the model, and the idea is to try and say something more intelligent about how this works. Thank you. Well, there are people in here that could answer that better than me. The physical, I mean, I can tell you what it does. I mean, why that, I mean, you know, and then I say it has a name, Ekman friction or something, so that therefore it, you know, it's historical. Does anybody? Okay, so let me say that, I'm going to partly say it this way. These simulations, well, I don't know if I want to go all the way back. These simulations that I've been showing here that Matt Chantry did, we did not introduce that alpha as part of the modeling that this last modeling that I was discussing. That's not why we introduced it. It was introduced already here. You have to introduce it here. And the reason is because you have stress-free boundaries, and you know, and so you allow the mode that is with no vertical variation, you know, so it's an allowed modes have no vertical variation. That satisfies the stress-free boundary condition, okay? It's non-zero, it satisfies the stress-free boundary condition. That mode, viscosity does not act in the wall normal direction, you know, and there's no viscosity acting in this direction. The only way viscosity can act is through variation in the horizontal direction to damp that mode. So what happens is if you have a long scale variation of that mode, it is damped very, very, very slowly. And that's very unrealistically because I mean, that wouldn't exist in a real channel. I'm not sure I'm answering it quite the right way. But what you would see is if you did not include that, there would be very, very slow decay back to laminar flow around all these patches, extremely slow because viscosity doesn't act on these constant vertical modes. So you have to introduce something that damps them. That term, it's 10 to the minus 2 is what we you know, again, not the modeling I'm talking now, just when Matt Chantry did this, we tested that up and down, lots of things, and it just didn't seem to make much difference, thank goodness. But it, I mean, it's a question, but if, I'm kind of lost my point. If you, well, just to say, if you don't include it, then what will happen is you'll just have these very long, very, very slow decays. Oh, I know what it is. What you could do is you can measure, what Matt did is he, let me see if I can remember exactly what he did. He fit that by looking at the decay. So you can get it by looking at the decay in actual plane couette flow. And other people have done this as well. So you do plane couette flow, you look at what the effect of the boundary layer would be on the decay of those modes, and you match this alpha such that it would give you the same thing. And that's the way he did it. And what you see is it only, viscosity dominates, you know, there's a viscous term. Viscosity dominates all the modes except for the ones that don't vary in Y and vary very, very slowly in the horizontal. I mean, I'm talking about a very long wavelength variation. Those are the only modes for which that term is at all appreciable compared to the actual viscosity. Yeah. Right. No, it does reverse. Okay, no, okay, it does reverse. So yeah, we should talk when Sebastian's here next week, because he's spent a lot of time studying that. It does reverse. It reverses at large scales. It reverses on the scale of the pattern. But and we should talk about that because we don't really understand it so well. I mean, he has the measurements. We know what the data tells us, but we don't know how to think about it.